Linear Discriminant Analysis, LDA, is a classical algorithm in machine learning that is used to classify data samples into one of several predefined categories. LDA is a supervised learning technique that is commonly used in statistical analysis, pattern recognition, and computer vision applications. The algorithm takes a set of training data and uses it to learn a model that can predict the class label of new, unseen samples. LDA is widely used for dimensionality reduction. LDA is a supervised learning algorithm, which means that it requires labeled training data. LDA is a linear classifier, which means that it can only separate classes that are linearly separable. Nonlinear separation requires the use of more complex models, such as kernel methods. LDA assumes that the covariance matrices for each class are equal. This is known as the homoscedasticity assumption. If this assumption is violated, it can lead to poor performance. LDA is closely related to principal component analysis, PCA, which is another linear transformation technique. However, while PCA maximizes the variance of the data, LDA maximizes the separation between the classes. LDA has a Bayesian interpretation, where it assumes that the data is generated by a Gaussian distribution and that the class labels are a priori probabilities. LDA has been applied in various fields, such as image processing, text classification, and bioinformatics. LDA aims to find a linear combination of input features that best separate different classes of data. LDA maximizes the ratio of between-class variance to within-class variance. LDA computes means and covariance matrices for each class. LDA finds linear transformation of input features that maximizes separation between class means while minimizing within-class variance. Assume we have a dataset of n samples, each of which belongs to one of k classes. Let X be an n into P matrix of input features, where each row corresponds to a sample, and each column corresponds to a feature. Let Y be an n-dimensional vector of class labels, where E is the class label for the ith sample. We can represent the dataset as a collection of k subdatasets, x1, x2, xk, where each subdataset contains the samples belonging to a particular class. The mean vector and covariance matrix for each class are given by the following formula, where mu I is the mean vector for class I, sigma I is the covariance matrix for class I, and ni is the number of samples in class I. The overall mean vector and covariance matrix for the dataset are given by the following formula, where mu is the overall mean vector and sigma is the overall covariance matrix. The goal of LDA is to find a projection matrix W that maximizes the ratio of the between-class variance to the within-class variance. The between-class variance is defined as the variance of the class means, while the within-class variance is defined as the sum of the covariance matrices for each class weighted by their respective prior probabilities. The between-class and within-class variances using these formulas. The optimal projection matrix W can be found by solving the generalized eigenvalue problem, where W is a p-dimensional vector representing the direction of the projection, and lambda is a scalar representing the corresponding eigenvalue. Once the projection matrix W has been computed, it can be used to transform the input features into a lower dimensional space. Given a new input vector x, the corresponding projected vector y, where y equals W to the power of tx. The advantages of LDA are dimensionality reduction, feature extraction, robust to outliers, can handle small nonlinear data samples and interpretable results. The limitations of LDA are it assumes linear separability and normality, overlifting, requires balance classes, limited to binary and multi-class classification, sensitivity of feature scaling. In the practical world, this algorithm finds usage in image processing, text classification, bioinformatics, finance, quality control, social sciences, marketing, medical diagnosis, environmental monitoring, sports analysis, etc. For conclusion, linear discriminant analysis is a classical machine learning algorithm that is widely used for dimensionality reduction, feature extraction, and classification. LDA seeks to find a linear combination of the input features that can best separate the different classes of data.